Okay, so this is the second video for our midterm review. Pages starts at page 18 in the non-calculator booklet. Number one says, what is the x-coordinate of the point of inflection of this graph? So for points of inflection, we need to find y double prime. That does necessitate us finding y single prime first, which if we take the derivative would be x squared plus 10x. And y double prime is 2x plus 10. Setting this thing equal to 0, we will actually be able to find possible inflection points. Solving out, we get x is -5. That happens to be the answer because there's no other choice, but let's just analyze something real quick here. Technically, we really want to draw a number line for the second derivative, put -5 on this number line, and test our second derivative. Before you get to -5, say -6, the derivative is negative. Say at -4, the second derivative is positive. So we do in fact have a sign change, which means f is concave down going to concave up. All right, number two is a question that we will get to, but not yet. It says the graph of a piecewise linear function from -1 to 4 is shown above. What is the value of, this is called the integral, the definite integral from -1 to 4 of f of x dx. And the meaning of this is something called the net signed area between the curve and the x-axis, similar to displacement. So we want to get the net signed area of the curve between the graph and the curve, or sorry, between the graph and the x-axis. So we have this triangular piece here, which has an area of 1 times 2 divided by 2, which is 1. This guy here is 2. This is 1. This is 1/2 in terms of area, but it's negative because we're below the x-axis. That's when we make signed area. If we're below the x-axis, we're going to be negative and -1. So adding the integral means add up all those areas. We would get 1 plus 2 is 3, plus 1 is 4, minus 1 is 3, minus 1/2 is 2.5. And again, that's something that we're going to be doing toward the end of next week. All right, number 3, we have the integral from 1 to 2 of 1 over x squared dx. This is something we'll also be doing next week. If you want to evaluate an integral algebraically, what we do is we actually find the antiderivative of x to the -2. Finding the antiderivative of x to the -2, we do the power rule in reverse. We add 1 to the power and divide by the new power. So our antiderivative would be -1 over x. And what we do is we evaluate -1 over x at 2 and then at 1 and subtract the 2. So we're going to have -1 over 2 minus -1 over 1, which is -1/2 plus 1, which is 1/2, choice C. And again, this is one where I'm starring it off. We have not done this yet, but in the anticipation that we get to it, which I think we probably will, this is something that could appear on your midterm. Number 4, f is continuous on the closed interval, differentiable in the open. Which of the following could be false? Well, if we take a look, f prime of c being equal to the slope at the endpoints, this is the mean value theorem. If we have differentiability, mean value theorem applies as long as c is strictly between a and b, so that's good. Part B, f prime of c is 0 for some c between a and b. Well, that is rolls. And for rolls to occur, we need to know that 2 points are equal. All we know is the function's continuous and differentiable. So perhaps we don't have that. Perhaps we have something like this, where the derivative, actually, let me just draw a little better, where perhaps the derivative is never equal to 0. So we don't know that that's true. This could be false. Having a min or a max is a property of functions on closed intervals. So for example, this function has a min here, a max there. This function has a min here, a max there. All continuous functions on the closed interval have a min or a max. And this is the integral. That means the area under the curve makes sense. The integral exists, the area under the curve exists, which in any situation where you have a continuous differentiable function, the area makes perfect sense. So that is not correct either. Choice B is correct. Whoopsie. Number 5. We have if x squared plus xy equals 10, then when x equals 2, dy dx is. So we have a function that's an implicit or an implicit curve, and we want to find the derivative at a certain point. So we will take the derivative with respect to x on both sides. Derivative with respect to x of x squared is 2x plus xy will require the use of the chain rule. So split this up. Here are my derivatives. Remembering the derivative of y is dy over dx. So we have x dy over dx plus y equals 0. And we want to solve for dy over dx. So we can move over these guys. So we get x dy over dx equals negative 2x minus y dividing by x. We get that dy over dx is negative 2x minus y over x. Now we want to find the value of the derivative when x is 2. So if x is 2, we would get negative 2 times 2 minus y over 2. But here's the issue. We don't know what y is. But we have the original curve to go back to, which is x squared plus xy equals 10. And if we plug in x equals 2 into this, that will actually yield exactly one y value. So we get 4 plus 2y equals 10. 2y is equal to 6. Y would be 3. So we can take this 3 and now put it over here. And evaluating this will give us negative 7 over 2. Final answer, negative 7 over 2. Choice A. So, number 8, this is a tough question. Let f and g be differentiable with the following properties. G prime of x is always positive, and f of 0 is equal to 1. Now they told us h of x is f times g, and h prime just turns out to be f times g prime. But here's what we know. If h is a product, we know how to take the derivative of a product symbolically according to the product rule. So if I had my f and g, my derivatives would be called f prime and g prime. We would just simply cross these and do f of x, g prime of x, plus f prime of x, g of x. But we're being told that h prime of x is just, if you notice, we're being told that h prime of x is just this first term. But we know from the product rule it's that term plus this guy. Well, if that's the case, then this circle term, the f prime of x times g of x, must equal 0. So we have f prime of x times g of x equaling 0 because it's not part of the derivative formula, yet we know it's supposed to be. That means that part has to be 0. And then they told us g of x is always greater than 0. So the whole idea is now we want to solve. We have f prime of x times g of x is equal to 0. Well, that would mean that either f prime of x is equal to 0 or g prime of x, g of x is equal to 0. And we know this is not true. This never happens. So that doesn't yield any solutions. But f prime of x being 0, so this means the derivative is equal to 0. If you think what that means about f, functions whose derivative is 0, whose derivatives are 0, are horizontal lines. They can be anywhere, at any height, but the slopes are 0. So f of x can really be any number, or just a constant. So f of x is a constant. Well, what constant is it? If f of 0 is 1, what that means is that if I look at the graph of this function, at 0 we're going to be at height 1. Well, since it's a constant function, that means everywhere else the height shall be 1. So we're really talking about the graph of f of x equals plain old 1, which is choice E. Tough question, especially when you kind of look at the choices and go, well, I could have just kind of guessed E and maybe gotten it right. That's a hard question. All right. Number 10, what is the instantaneous rate of the change of the function at x equals 2? Instantaneous rate of change, or IROC, is the derivative So we have f of x being x squared minus 2 over x minus 1. If we would like to take the derivative, we will need the quotient rule. So I'll come over here, take our individual derivatives as we do, and then low d high. So low d high is x minus 1 times 2x minus high d low, which would be minus parentheses x squared minus 2 times 1, technically, over low squared, x minus 1 squared. You could simplify this a little bit if you'd like. We can distribute the 2x and get 2x squared minus 2x minus x squared plus 2 over x minus 1 squared. Or you could just plug in the 2 up here, but we'll simplify anyway just for practice. We will get x squared minus 2x plus 2 over x minus 1 squared. And we're being asked to, I believe, find f prime, or the slope at 2. So we will do that. F prime at 2 is equal to 2 squared minus 2 times 2 plus 2 over 2 minus 1 squared. The bottom just turns out to be a 1. The top turns out to be 4 minus 4 plus 2, 2 over 1, which is just plain old 2. That doesn't seem very satisfying either, but that's the answer. All right, number 12, we have a limit problem as x approaches 2. And notice it's a piecewise function that breaks up at 2. So what we want to do is really ask ourselves, well, what is the natural log of 2? And does it match up with 2 squared natural log of 2? Well, this is 4 natural log of 2. Clearly, natural log of 2 is not equal to 4 times itself. So the limit does not exist. This is the whole Shutter method where you really have to come. This is approaching 2 from the left of the function. This would be the limit as x approaches 2 from the right of the function. Okay. So non-existent is the answer. Number 13, the graph of this function shown in the figure above has a vertical tangent at 2, 0. So we have a vertical tangent. Actually, let me not draw that. I'll draw that as a, I don't want to draw that as a dotted line. I don't want people thinking it's some sort of bizarre asymptote. So there's my tangent line. And the horizontal tangent's at 1, -1 here, and 3, 1 there. For what values is f not differentiable? Not differentiable means on a graph, corners, cusps, vertical tangents, because vertical tangents don't have an actual numerical slope attached to them, and discontinuities. Those are the 4. So we see we have a discontinuity at x equals 0. We have a vertical tangent at x equals 2. And no corners or cusps. So we just have those 2 at 0 and 2 only. Choice B. Very easy question. Number 14, a particle moves along the x-axis. So its time, whoopsie. Position of time t is given by that function. For what value t is the velocity? 0. If I have position, the derivative of position is the velocity. So that's 2t minus 6. Set that equal to 0. 2t is equal to 6. T is 3. And we're done. Simple as that. 16, f of x is sine of e to the negative x. F prime of x is. We have sine of e to the stuff. This is a double chain rule problem. So first we have sine of stuff. Derivative would be cosine of stuff. Then we must multiply that by the derivative of the stuff. Well, now we're working with e to the stuff. Derivative of e to the stuff is e to the stuff times the derivative of the stuff. Derivative of negative x is -1. This is where everybody forgets this. Everybody forgets this. This is the important one that everybody misses when they do this. So f prime of x is equal to negative e to the negative x, cos of e to the negative x. Choice 5, or choice E rather. Next one, the graph of a twice differentiable function f is shown above. Which of the following is true? I actually think we've done this question before, but we can do it again. So if you notice, they're trying to compare f of 1 to f prime of 1 to f double prime of 1. Well, f of 1 is just the height. This is the graph of f. Oh, this is where people get confused, I remember now. Twice differentiable just means f prime and f double prime exist. But we are still looking at the graph of f. So let's not get confused there. F of 1 is the height at 1, which is 0. Now, f prime at 1, f prime at 1 is the slope at 1. If we look at the slope of 1, it's pointing upward, it's positive. And f double prime of 1 would refer to the concavity. Well, we are on a sad-faced track here. We are concave down, so the second derivative is negative. So if you think about this, if we're trying to list them in order, the second derivative would be the most negative, followed by f of 1, which is 0, followed by f prime at 1, which is positive. So choice D is the correct answer here. We have we want the equation of the line tangent to y equals x plus cos x at the point 0, 1. So we've done a lot of these problems over the year. Y equals x plus cosine of x. We want to take the derivative. This will help us find the slope. So derivative of x is 1, and the derivative of cosine is negative sine. We want to write the equation of the tangent line. So I usually start off by doing this, but I decided not to this time. So we know a lot of things. We know y1 is 1. We know x is 0, so I'll just write that. We just need to find the slope. Well, we have the derivative, which is the tool to find the slope. We want to plug in the x value of 0, 1 minus sine of 0. The sine of 0 is 0. So the slope is 1. Y minus 1 equals x. What form do they want this in? It looks like they will solve for y. So we'll add 1. Y equals x plus 1. Choice B. Boy, that's a very easy question. Very easy. All right. 19, if f double prime of x is given by that function, we want to find out where the graph of f has inflection points. So first, I want to set this thing equal to 0. We would get 3 roots. X is equal to 0, x is equal to negative 1, x is equal to 2. We have f double prime. We want to find inflection points. So this is as simple as drawing a number line, putting our critical value, or putting our roots on it, and figuring out the signs in each interval. Some of you can do this in your head. So let's see what we have. Before we get to negative 1, negative 2. X is negative. Negative 2 plus 1 is negative. Negative 2 minus 2 is negative, but squaring is positive. In fact, that's always positive. I'm just going to put a circle positive there. So we have a negative times a negative, which is positive, times a positive, which is positive. Pick a number between negative 1 and 0, say negative a half. X would be negative, but negative a half plus 1 is positive now, and the squaring is always positive. So negative times a positive is a negative. All right, plugging a number between 0 and 2, I like 1. 1 is positive. 1 plus 1 is positive. 1, and then the other part is positive always. Here we go. And past 2, 2 is positive. 2 plus 1 is positive. The squaring is always positive. Here's our number line. F is concave up from negative infinity to negative 1, concave down between negative 1 and 0, and concave up everywhere else. So there are only 2 inflection points at negative 1 and 0. Okay, real quick, I mean, you could do this question in 10 seconds if you recognize x minus 2, the squaring will not produce a sign change. This is akin to like when you're graphing a polynomial last year with Mr. McCarville, that you bounce off as opposed to crossing through the asymptote. Across this. Let me say this again. It's akin to bouncing off the x-axis as opposed to making an actual sign change. You would not get an inflection point. All right, number 22, here's our function. Where is f increasing? Well, we need to find f prime to do this job. And we need to find out where f prime is equal to 0. Factoring out a 2x, we'll be left with 2x plus squared plus 1 is equal to 0. Didn't know how to factor there for 3 seconds. So we would get 2x is 0, or 2x squared plus 1 equals 0. 2x squared, so obviously here x is 0. And then 2x squared is negative 1, x squared being negative 1/2. But x squared can't be negative, so this has no solutions. And so we have x equals 0 being the only critical value. So we'll make our number line. Our derivative is 2x, parentheses 2x squared plus 1. 2x squared plus 1 is always positive. And so 2x would change signs at 0, being negative, then positive. So we want where the function's increasing. If f prime is positive, we know f is increasing on the interval 0 to infinity. Choice C. Next question. 23. We have the graph of f shown above. Which could be the graph of the derivative? Very easy question. I always say look for the 0 of the derivative. Where is the surfer dude going to flatten out? The surfer dude flattens out just after the origin. That's the only place it flattens out. So A could work. We have a 0 there. B does not. C could work. D does not. And E could work, perhaps. So we're down to that. So just by knowing that, you're down 2 choices here. Then, well, we are increasing till we get to 1. Decreasing after that. So our derivative is going to be positive before 1, negative after 1. So positive before 1, negative after 1. We can eliminate C. Now, what's going on with the derivative? This is where we need to make a choice here. Well, if you take a look, before you get right about here, we have an inflection point. So what's happening is the derivative, the slopes are increasing until you get to that point. So slopes are increasing until we get to that point, and then they slough off to get to this maximum on the graph. So the slopes slough off, so choice A is the best choice out of the 2 that are left. Next one. This is a bit of a tricky question. The maximum acceleration attained on the interval 0 to 3 by the particle whose velocity is given by that function is. I just want to do a little side question here. If I asked you to find the maximum of, say, f of x is x squared plus, I'm making this up now, x squared plus 6x, you would take the derivative. So you would look at the derivative of the function you were trying to max out, 2x plus 6, and you would set that equal to 0 and find the critical values. So if I want to find the max of f of x, I look to its derivative. So if I want to find the max of acceleration, I want to look to the derivative of acceleration. We were given velocity, though. So we were given velocity. So we can get acceleration by taking the derivative of velocity, which is 3t squared minus 6t plus 12. But now I want to get the max of the acceleration. That tells me, it says take the derivative of acceleration, which is going to be 6t minus 6. So 6t minus 6 equals 0. 6t equals 6. T is 1. Now, this is where the max acceleration could occur. Well, that's actually a critical value. Let's be careful here. We are in a closed interval, so we also have to test the endpoints. So here would be a good place to compare our accelerations at 0, 1, and 3. And this is where you can make a little t-chart and just compare. I want to figure out where I have max acceleration. So now I'm going to go back. I want to plug my endpoints in, plug my critical points into the acceleration, and see which one is the biggest. So my t-value is 0. I'm plugging into acceleration. 3 times 0 squared is 0. 6 times 0 is 0. 12 is the acceleration. At 1, 3 times 1 squared is 3. Minus 6 is negative 3. Plus 12 is 9. That's not the max. And then 3. 3 squared is 9 times 3 is 27. Minus 6 times 3 is 18. That's 9 plus 12 is 21. There's the winner. That's the maximum acceleration. So actually, if you didn't go through this whole rigmarole of finding the derivative and finding the critical value, you would actually have not got this wrong, but I would have been very lucky. All right, 26. Our function is continuous on the closed interval 0 to 2 and has values given in the table. The equation f of x equals 1/2 must have two solutions if k equals. So here's what we have. And I believe we've done problems almost exactly like this. X equals 0, f of x is 1. So we have this point on the graph. And we also have the point 2, 2. And they're asking us to say, hey, 1, what? I'll make it a smiley face. Where should we be able to put this point so that the equation f of x equals 1/2 has two solutions? Well, f of x equals 1/2 looks like this. So right now, if we kept the smiley face where it is, we would have, like, say, 0 solutions. So we want this thing to have two solutions. So if you think what could happen, I want the graph to intersect the green line twice. So I would have to really take my point, move it below the green line, and then if I want to connect all three of these points, because the graph is continuous, I would really have to dip below that line 1/2, and then I would have two solutions. So I need to dip below the line. 1/2 would dip me exactly on the line where I could kind of just cheat and only have one solution. 1, 2, and 3 are all no good because they're not below the line. And 0 is the only y value below the line. So if I had a 0 here, I would get 1, 2 intersection points. Choice A is the answer. All right, whoops. 28. If f of x is tan of 2x, then f prime of pi over 6 is. Well, f of x is tan 2x. I need to take the derivative of that. Derivative tan of stuff is secant squared of stuff. Yes, you can't forget all this stuff. You can't forget these rules. Times the derivative of the inside, which is 2. That's the chain rule. So we get f prime of x is 2 secant squared 2x. Now, what's interesting is we have to find f prime of pi over 6. And some of your trig scares me a little bit occasionally. F prime of pi over 6 would be 2 secant of 2 times pi over 6 squared. So from here we get 2 secant of pi over 3, that's what 2 times pi over 6 is, squared. Pi over 3 is 60 degrees. So we're going to sketch a little 30, 60. I'll sketch it the other way. Sorry. Oh, that's good. Sketch it that way. What am I talking about? 60, 30, 90. Across from 30 is a 1. Across from 60 is root 3. Across from the 90 is 2. So secant is the reciprocal of cosine. So if I think of SOHCAHTOA, cosine is adjacent over hypotenuse. I want to take the reciprocal of that. So secant of pi over 3 is the hypotenuse over the adjacent. Hypotenuse is 2 over 1. Hypotenuse is 2, adjacent over 1 adjacent is 1. So secant is 2. So here we go. We have 2 times 2 squared. 2 squared is 4 times 2 is 8. There's our final answer. Choice B. And that's it for this video.